Perfect. Okay. So, before I start today, I'm going to have to put on some safety gear because, as we all know, the most attractive thing is safety. So, we're going to stay safe today. I'm going to be dealing with some dangerous substances, mainly fire. So, I have my protective water, just so everyone knows. And I also have this beautiful, beautiful towel to smother some flames. So, never fear, we will be completely safe today. So, we're just going to get motivated. And, you know, a lot of people say you need to light a fire under someone to motivate them. So, I'm just going to light a fire. And hopefully that motivates us to do some thinking. So, a cool thing happens, actually. I don't know how many... Anybody drink tea? Mm-hmm. Drink tea? Tea? Wonderful. This is... Does anybody know what shape a tea bag is? No, probably not. It's actually kind of cool. It's a cylinder. So, a tea bag unfolds, actually, to a nice little cylinder. And that's kind of cool, and so we're going to deal with that later. But for now, I'm going to light it on fire. And I just want you guys to think. So, you can see it burns. Burns pretty well. And it goes pretty quickly. Hopefully, it goes past the tongs there. Now, that was really quick, and it happened in an instant. But I want you guys to think about that fire for a second. Hopefully, I don't get ashes everywhere. I know, I've wasted so many tea bags, but it's worth it because we are going to talk about some cool stuff today, all right? So, here's my question. I lit that tea bag on fire. What happened around the tea bag? Right? So, holding in the tongs, right? I had the tea bag. Let's pretend this is a tea bag. The flames were pretty small, but still you see some change. And so my big question is, what happens when you light a fire? So, anybody here camp? I'm assuming we got some campers here. You're camping, it's like 10 o'clock on a cold Alberta night. Why do you light a fire?
To release heat. To
release heat, because it warms you up. Also, you know, cooking marshmallows, s'mores. Kind of a big thing. But most importantly, all right, the fire heats the air. So what we're doing is we're warming up the air, we're warming up the gas. Okay? In the summer, who here, hands up, who here lives in a basement? Who here lives upstairs? Okay, we're all like children living in our parents' houses. So, sleeping in the basement in the summer is the best because you get all that cold air. And the rest of that hot air ends up rising. You've probably all heard this, hot air rises. It's kind of a well-known thing. So, big question that we're going to address today, why does hot air rise? That's the big question. So, what have we been talking about in class? The ideal gas law.
Well, we had the ideal gas law.
The ideal gas law, of course. So, can anybody remind me what the ideal gas law is? Anybody?
Is it PV equals energy?
Yeah.
Pressure times volume equals moles times our gas constant times temperature. So, question for today, how do we take this equation and use it to explain why hot air rises? Well, let's think about fluids, things that float. We talked about this would be like grade 9. Why does something float? Yeah.
Because less dense than the thing it's on top of?
Perfect, that's what I was looking for, density. Is density in this equation? Does anybody remember what density is, if we were to break it down?
Mass on volume.
Exactly. So, we'll write off to the side. We're going to use our density. This is a cool little thing. It's called rho. It's a Greek letter, and it's our density equals our mass over our volume. So, we're trying to find this in there. Well, do we have volume? Obviously, it's right there. Okay, so now we need to find mass. Do we have mass in this equation? Can anybody see where we might find mass?
In the moles?
In the moles, exactly. If I gave you the mass, how would you find moles in an equation?
The molecular weight of a compound.
Right. We have something, a beautiful periodic table of elements that gives us molar mass. And another thing we can write over here is that moles, N, equals mass divided by big M, molar mass. So I'm going to rearrange for that and see if we can't find density after all. All divided by big M. Okay, anybody, quick rearrange, can anybody solve for density for me? You think we could do that?
Mm-hmm.
I'm going to assume some bright young kid solved for me.
I can do it.
And we end up with this equation. So, we got mass over volume. That's density. That's exactly what we were trying to find. So let's just move over here and let's write this really big and let's do some analysis of density. Okay? So, when we have this big equation here, we're going to change things. Are some things in this equation constant? Or do they all change? Some are constant. What's a constant over here?
R.
R. Exactly. It's our gas constant. So already we don't have to worry about R. Anything else a constant?
The pressure and the temperature should be constant unless we're changing the temperature during the fire.
We are changing
That's
because what we talked about when we light the fire. So what happens when we light the fire? Temperature increases.
So molecular weight.
Well, yeah. What about molar mass?
Molar
Molar
mass.
mass is a constant on our sheet. And let's think about pressure. Who thinks? Hands up. Let's go. If you think pressure is a constant, you're going to give me a thumbs up. If you think pressure is going to change, give me a thumbs down. Ready? Thumbs up. Perfect. Pressure we're gonna treat as a constant here. Okay. So because it's such a big room and nobody's like opening the door or changing our pressure in the room, we're gonna assume that that's a constant. So I'm gonna write this just a little bit nicer because we've discussed that pressure, molar mass, and R are all constants. So we're left with one variable. All right, and that one variable is temperature. So what happens when we change it? That's the big question. So let's start, I don't know. If we increase T, that's the big question. We'll do thumbs again. If you think I increase T, if density increases, we'll go thumbs up. If it decreases, we'll go thumbs down. And thumbs up. Sorry, temperature we're going to increase, like we light that fire. Is our density going to go up or down? Down. That's pretty good. Oh, we got enough. So, let's think about this. This is a little tricky because you'd say, well, I increased over here, so why isn't this increasing? Okay? Well, mathematically, our temperature is in the numerator. So, let's take a little example here. Let's go 1/3. Now, if I increase 1/3, I could just add 1 to that 3, right? So I go 1, 3 plus 1 equals 1/4. What's bigger, 1/3 or 1/4? Anybody?
1/3.
1/3 is bigger. So if I increase the bottom, what ends up happening is it actually gets larger. Okay? So we can look at this equation as a left-hand side and a right-hand side. And they are, thanks to this beautiful, beautiful sign, they are equal. So we increase T, our whole right-hand side decreases, so our whole left-hand side has to decrease. So, can anybody state the correlation between temperature and density for me?
Inversely proportional.
Right. So let's expand that out. Let's use a few more words. So as I increase temperature, and then someone finish that for me.
The density decreases?
The density decreases. Now let's think about the opposite. As I decrease temperature,
The density increases.
the density increases. Perfect. So now I'm going to light some more stuff on fire. All right? So, I feel like such a fool. I didn't put these safety glasses on. But I'll put them on for this next portion. So, what I'm going to do this time is I'm going to light the tea bag on fire again, but I'm not going to hold on to it with my tongs. So I'm going to need some quick predictions as to knowing this correlation between temperature and density, and knowing what we know about density and fluids. When I dump this out, what's going to happen? Can I get some guesses from the class? When I light this on fire, what's going to happen? Any predictions? You look like you've got a guess.
She's going.
You've got a guess?
The temperature's increasing, so the density's going to decrease. That's going to go down.
Right. So what's going to go down?
tea bag?
The tea bag. Okay. So we think it's going to go down. Any other guesses?
When it rise, when
Hey.
it rise up, because hot heat will make it rise.
Okay, yeah, that's another guess. So it might rise. All right. So who thinks we'll go thumbs up? It's going to rise. Thumbs down.
I don't really think
It's going to
so
go
long
down.
enough.
And thumbs. 3, 2, 1. Got a couple up, couple down.
A couple more.
Okay, everybody, just be ready. We'll see what happens as I light this beautiful, beautiful fire. Okay? Oh,
Oh, please fly.
oh my goodness. What's happening?
Oh,
Breathe
yes! Oh, yes! Oh, gosh,
my
no.
goodness. Wow. Okay, so who had that guess right? Hands up, who had that guess right? Wow. Okay, now there were a couple things there. It was pretty cool. I will admit, I've hit my roof at home probably 6 times with a tea bag. So I was kind of curious to see how high it would go. Probably take these off. So, why did it fly up? Well, we just talked about it. Temperature went up, density goes down.
It just moves down, obviously.
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 So,
Great.
our less dense fluids get shot upwards. Now, here's an interesting question. Why didn't it shoot up instantly? It burned, I want to say, 7/8 of the way down before it shot up. So does anybody have a guess as to why it didn't fly up automatically?
Because the density of the tea bag was greater than the actual weight of the. I know how to explain this, I just can't.
I think you got it. Keep going.
Basically, once the density had become equal to the other side of the equation, it would be maintaining its level, and then as the temperature increased, the density became less and it ran.
Very good. Yes, very good. I'm just going to summarize that. So basically, the tea bag still has mass to it, right? We still have to take into account that gravity is working on that. So the force of the density rising has to surpass the force acting on the mass, and then it'll shoot up. So that's an interesting one. Another question, when we lit it on fire, it stopped, like the flame stopped, but the tea bag still kept rising. Why did that happen? So we have flame increasing temperature, flame's gone, why does it keep to rise? Why does it keep going up? Any guesses on that one? Yes? You moved your hand? No?
Mm-mm.
So, let's think about it. The fire increased our temperature, so we know we have less density. But, when the fire goes out, does our temperature just immediately drop?
No.
No. So, even though we don't have an acting fire raising the temperature is still higher, and it'll just slowly work its way back to room temperature. And that's why we saw it fly up, hover, and then slowly work its way down. If it just stopped right after fire, we would have seen it drop at the speed of, well, acceleration of gravity. So that's a good one to continue. All right, and I think that's actually all I have. So any questions regarding this demo? Any questions regarding the level of density, or can we move on to some calculations?
Yes.
Yes? Perfect. I'm just kidding. We don't have calculations.